10E and 10F. Study lesson on Friday, if we're available, and then next week we're going to do 10G, and I'll give you time for the chapter review. That's the plan. So you don't need to be connected to this, and you don't need your computer up. You can be listening, and you don't need to be typing, and you don't need to be staring at your screen. And I'm looking at one table in particular. Okay, cool. Yes. Excellent. So, Eulerian graphs. Remember we talked about Euler and Euler's formula last lesson. Euler's formula, V plus F minus E equals 2. Vertices plus faces minus edges equals 2. Well, that was a couple lessons ago, I think. Eulerian applications is a pretty simple one. I'm going to run through this and the next lesson in one go. They're both very similar. There's one little addition, and then I'll give you time to do it. Each of these have a couple of questions, so they're pretty easy. Whiteboard video associated with both, so keep that in mind. In some situations, the vertex is important, and the edge just facilitates travel. So we're talking about context now. If you might get a context where the edge doesn't matter. The edge is the road between towns. What matters is the towns that you get to. In some situations, it'll be the opposite, and that'll be our next lesson. So in this lesson, it is the edge that we care about. We're talking about the edge in particular. So consider mowing schedules. So this is a bit of a hot topic at the moment. Laying NBN cables, also a hot topic. So NBN cables, the matters, but the edge probably matters more because that is the cable. The setting up a marathon course, the edge matters because that's where people are running, etc., etc. And in fact, the vertices there might just be matter nearly as much. So there are going to be different situations where you'll be using graphs for different things. An example, take the graph on the right. Is it possible to travel along each edge just once? Where do I need to start and finish? So here's a graph. Who would like to suggest a vertex that I start on? E and C, I've heard. I'm going to start with C. I'm going to travel around this graph and see if I can travel along each edge just once. So starting at C, I'm going to go to D, E, to A, to B, but then I'm stuck back at E. So maybe I'll do it the other way. Maybe I'll work that out. No, now I'm stuck at C. Okay. Do you think I can do it? The answer is I can't actually do it. If I start at C, I can't. But if I start at E, this is why I chose this order, so thanks for both suggesting. If I start at E, I can go E to B, B to C, C to D, E to A, E to B. I start at E, I finish at B, and I've travelled along every edge. Why can I start at E and do this, but not at C? Why is that the case? Okay, thank you, Flynn. So C, and by C I mean E, my apologies. E has 3 vertices, which makes it a good place to start. Now, it might seem like E is the thing that makes this possible, but the 3 vertices is actually a hindrance to our situation. C is a good vertex. It's got 2 vertices, 2 edges running into it, whereas E is a bad one. It causes a bit of a problem. Because imagine this, if I don't start at E, I can go into E, out of E, but then I've got this extra edge, which I now can't access without repeating an edge. Does that make sense? The only way I can deal with edges is if I either start or finish there. Because if I start there, I go out and I don't need that in first. So I can make the odd number of edges into an even number. If I finish with B, I can go in. So if I have an odd degree vertex, it can be part of what's called an Eulerian graph or a semi-Eulerian graph, but I have to start at the odd degree vertices or finish at the odd degree vertices. And because I have the odd degree vertices, they can't be in the middle, it means that I can have at most 2 odd degree vertices. If I've got a graph where I've got 4 odd degree vertices, there's no chance I'm going to make it around that whole graph without repeating edges. Can I have a graph that's got 3 odd degree vertices? Can you tell me why not? That's all right. Any takers? Oh, I mean, the answer is I've led you down a path. The answer is obviously no, I can't. Why can't I have a graph that's got 3 odd degree vertices? Yeah? So if I have 3 odd degree vertices, it won't be Eulerian, which we'll get to that definition in a minute. I can't do a full root around, you're right. But I can't, like I challenge you now, draw a graph in your book that has exactly 3 vertices that have got an odd degree and the rest of them have got even degrees. You can't do it. Can you tell me why you can't do that? If I draw a graph up on the board, and sorry if anybody's watching the video, draw a graph, I might have 4 vertices and I want to make 3 of them odd. When I create an edge, what happens to my degree? This one goes up to degree 1, this one goes up to degree 1. One edge, how many? 2 to the degree. If I create this edge, I've now got 2 here and 1 there. I've got 2 degree vertices, but I've got 2 even. If I draw this one now, that becomes 3 and that becomes 1. I've now got 4 odd degree vertices, not 3, 4, and this is not Eulerian. I can't travel along each of them because I've got too many odd degree vertices. But I can't ever get 3 odd degree vertices. If I say, well, you know what, let's make this one a 2, so I've only got 3 odd degree vertices left, so I go out here. When I connect it to another one, that also becomes even, which means I'm now down to 2 odd degree vertices. I can never get 3 odd degree vertices because that means I've got a total degree of an odd number, but each edge creates 2 connections. So the total degree has to be even, otherwise. So this, what you're going to find with this topic, in my opinion, is that as you're going through it, it's very definitional and the questions are fairly trivial in most cases. They're pretty easy to do. This chapter is full of simple familiar questions. So if you're, when and how does this get complex? Well, there's one right there. How come we cannot have 3 odd degree vertices only in a graph? And you have to be able to explain that. That's a harder question. And I want you thinking about that. Anyway, so the point here is I've got 2 odd degree vertices here, E and B. So as long as I start at E and finish at B, I can go along every edge exactly once. But if I start at A, D or C or finish at A, D or C, it won't work. That's the main takeout from this lesson. What about if I add a path from A to D? So this one here I can do. I've shown you I can do it. Can I do that? I've got my degree of A equals 3. Degree of E, I might just zoom in on the path. Degree of E equals 3. Degree of B equals 3. Degree of C equals 2. And degree of D equals 3. I've now got 4 odd number vertices. And based on what we've just talked about is we have to start at an odd, we have to finish in an odd, but then the other 2 odds are going to have to be in the middle. There's no way I'll be able to do one full pen stays on paper, roll around this graph and cover every edge without repeating an edge. No chance. So here we go. A to B, E say, E out to D. This is good. I've covered D. E's done. D to C and C to B. I've covered C now, but now I'm stuck at B, and I'd never covered this edge. So that extra edge means that I go from 2 vertices that are odd to 4 vertices that are odd, and now I cannot do this question. Is that okay? All right. Summary. And this you'll want to write down at some point, but not now. I'm too quick. The summary is the degree of the vertices matters. If I have 2 odd degree vertices only, it worked. If I had 4 odd degree vertices, it did not work. And down here, number of odd degree vertices. They're all even. All the vertices are even. This is called an Eulerian graph because it contains what's called an Eulerian trail. I can travel from one vertex a full roam around the graph, covering every edge exactly once, and finish where I started. So that's a complete trail. It's called an Eulerian trail. Here's one odd degree vertex. I've written there, draw me, go on, I can wait. You can't do it. Not possible. This trail, so the zero will be 2 odd degree vertices. There's an example. If there's 2 odd degrees, then it's called semi, and it's an open trail. You cannot start and finish at the same place, but it must start and finish on the 2 odd degree vertices. Doesn't matter which order. Here's one that's got 4 odd degrees. It's not Eulerian or semi-Eulerian, and that's how we say it. We say it's got 4 odd degree vertices. Therefore, it is neither Eulerian or semi-Eulerian. About Eulerian graphs, we're talking about the edges. Think about that for a second. Eulerian doesn't sound like it, but edges does sound like it, and it starts with an E, so there's that match. And here's my last little thing before we finish. This was the homework from last lesson. Maybe you had to go to it, maybe you didn't, but I drew here and I did green dots to represent the walls, the doors. A house contains 5 rooms. Each room has a door on each wall. That goes through each door exactly once. You may start, finish anywhere, or you can go outside. So the trick here is to understand that the rooms are the vertices and the doors are the edges. And I want to travel through each door, every edge once, without transporting myself from a vertex to another vertex or whatever, And so if I start here, let's say I start here, and I could travel in there, down here, travel back to here, there, around, through here, out there, back through here, down there. This room's now done, which is good news. Here, I'm starting to see a problem. That's all good. I've got a problem there and there. We'll look at the 5 vertices, which are the rooms. Let's have a close look at them. Well, in fact, there's 6 vertices here because the outside is another vertex. This room has 4 doors, has 5. This room has 4. This room has 5. This room has 5. And the outside has 9. So there are vertices, 4 of them. Therefore, it is neither semi-Eulerian or Eulerian, and I cannot travel from one position on this graph the whole way around only once. Any questions? So I imagine right now you're thinking, man, this stuff is riveting. But hopefully you're also thinking, but it's not too bad. I can do it. It's just a set of rules. Can you define Eulerian and semi-Eulerian graphs and trails? Can you explain why closed or open trails exist in some cases? Can you classify graphs as Eulerian or semi-Eulerian once you've done those exercises? And a reminder, the additional exercises I now haven't done answers yet. I might do them today. So they are available to you, basically because the textbook only has a couple of questions. So I'm actually going to leave you now. I'll bring you back when the bell goes, and we'll do Hamiltonian graphs, which is the next exercise, and it's also not bad. And and then we're almost done what we need, and we've almost done all of it in class, which is good. Cool.